Hello together. I want to present you some investigations within the TRR 188 about the load path dependent fatigue capability of forward rod extruded case hardening steel 16MNCRS5. At the start, I will give you a brief overview of the basic structure of the presentation. I will start with the motivation, come then to the materials and methods that were used, then discuss some of the results, and at the end, I will give you a short conclusion and an outlook. Yeah, what is the basic idea behind the project? The basic idea is that due to an economical production in these times, there's an increasing relevance of climate change and resource scarcity, which results in increasing demands on energy efficiency, emissions, and resource conservation. Because of that, metal forming has a high potential for lightweight construction, high cost effectiveness, and resource efficiency. But the problem with it is that right now the component design of components that are formed by metal forming, they are often based on using simple mechanical properties like from tensile tests or the use of safety factors. And because of the use of safety factors, we can't use the real potential for the lightweight construction. Because of that, we have like the damage control forming process within the project, where we look at the damage that we induce by metal forming and improve the utilization of the lightweight construction potential by evaluating this damage by the forming process. I will describe in a few seconds what damage is for us, and then we can lower the safety factors so we can use the lightweight potential. So what is damage? In our project, we define damage as forming induced damage, where the source material, for example, the 16MNCRS5 has manganese sulfide inclusions in it. And by forming, it can happen that there is a formation and growth of pores, which can lead to a coalescence or in some drastic cases to failure. And to quantify the damage by metal forming, the colleagues done in the past some investigations, for example, with the SEM 2D investigations of cross sections, where we quantify the pores, the number of pores and the size of pores, or by density measurements, so we can get a number of the forming induced damage. The problem with it is we only get like a quantification in 2D or like the density, but we don't know anything about the distribution of defects, which is very important for like fatigue fracture mechanisms or fatigue in general. So the basic questions is, how big is the impact of the forming induced damage, or how do we quantify it regarding the axial torsional performance? Now I'll give you an overview of the material because it's important in this case. The base material is the case hardened 16MNCRS5 with the following chemical composition weight percentage. And it has to be noted that it's forward rod extruded. And after the forward rod extrusion, the semi-finished product, which can be seen here, get like the final specimen geometry. It's a very well thought geometry because the only difference between different damage states, like from different extrusion angles, is the forming induced damage inside the specimen. Because through simulations, the strain hardening, residual stresses, dislocation densities, etc., are same. So we have like a shoulder opening of 30 degrees and 90 degrees from the extrusion process. So we have two different damage states where the only difference is the forming induced ductile damage within the specimens. How do we investigate the influence? We use, on the one hand, the testing systems, in this case, Walther and hydraulic testing systems for the axial torsional fatigue test. We use strain ratio of -1 and test frequency of 0.01 Hertz. And we also look at the load path dependence, where we look at the phase shift between the axial and torsional stresses of 0 and 90 degrees in this case, due to the time. And after that, we use a specific FIPSEM XP550L from size to investigate the microstructure. So I will show you some results. In this case, we look at the specific damage state of 30-degree shoulder opening angle. This is the state with less forming induced damage due to the forming process. And we tested it with a strain ratio of -1 and a total strain amplitude of 0.025 with a test frequency of 0.01 Hertz and an angular amplitude for the torsion about 10 degrees. And in this case, we don't have a phase shift. We look at the resulting force after the strain controlled fatigue test, and we can see that for a shoulder opening of 90 degrees, the response of the load is much higher. When we look at the torsional responses, like the torsional moment, we can see that in all cases, we have cyclic softening, which is typical because we have a cold-formed component. But we can see that the cyclic softening is much higher for the specimen without the phase shift. And we can see that the phase shift of 90 degrees, so that the torsion is after the axial stress, that the fatigue performance is increased, or we have a higher number of cycles to failure. By comparing two different damage states with comparable test parameters, in this case, we see a total strain amplitude of 1% for the 30-degree shoulder opening angle with less forming-induced damage, and the 90-degree shoulder opening angle, where we can see a slight difference in the fatigue capability, and the same for 0.25% total strain amplitude. So here we can see that the microstructural response or the material response is comparable throughout the damage states, but we see that the shoulder opening of 30 degrees with the less forming induced damage has slightly better fatigue performance. But it has to be noted, we're looking at the low cycle fatigue range, where the influence of this damage isn't that big in comparison to the high cycle or very high cycle fatigue range, because we have a more ductile fracture in the low cycle fatigue range due to the high strains. But we can see that the fatigue performance is improved through the damage control in the forming process. But there's also the problem how to evaluate the influence of these defects regarding fatigue behavior. Can we see an impact on the fatigue fracture or like the fatigue performance in the microstructure? For that, we used the FIBSEM, where we looked at the fracture surface. This is just an example of a total strain amplitude of 1% and with a phase shift of 90 degrees, where we can see that we see in the near surface area that the crack initiation is mainly focused around pores or manganese sulfides that are breaking due to the metal forming or due to the fatigue. And on the whole fracture surface, we see open manganese sulfides or a decohesion between the matrix and the sulfides. And we can see on the one hand, the typical fracture surface of fatigue specimen with a mixture of ductile fracture and fatigue fracture regions, that the cracking occurred, or the crack initiation mainly occurred at pores and manganese sulfides near the surface area, as well as that crack propagation along the manganese sulfides and pores. But how do we get the information about the distribution of defects in the volume that I've talked before? And for that, we had a new idea where we use the FIBSEM and ablate 20 nanometer of the material and take new pictures. This we reproduce many, many times, in this case, 510 times. And with this information, we try to get like an idea about the distribution in the volume. But the other important thing is how to separate the sulfides, like here, from the pores, because they're different and we want to get the numbers for both. And for that, we use the AI, in this case, the Zeiss Zen Analyzer software. And we use the in-lens pictures, which are a mixture of SE and BSE, and the SE pictures to segment the pores and the sulfides. By training the AI, it was at the end very good, so we can separate it very easily and very fast, and with a high accuracy. And after that, we try to get this information from the segmented images and convert it to a 3D model. In this case, it's a small model of a shoulder opening of 30 degrees, where we can see that the sulfides are not like a needle form, but like plate structures within the volume. And we can see that the pores are located in the whole volume and not only at the manganese sulfides. That was like the idea that we had before. And by only looking at the pores, we can see that the biggest pores are located near the manganese sulfide, but we have many nanopores that are distributed in the whole volume. And by comparing it to a 90-degree shoulder opening angle, we can see that there we have much more pores. Right now, we are like investigating this and quantify it, but we can see that, like to give you a number, that we have 27% more pores in the shoulder opening of 90 degrees in comparison to the 30-degree shoulder opening angle. And with these models, we can, for the first time, give a quantitative comparison of the damage states for whole volume and get an idea about the 3D pore distribution as well as the manganese sulfide distribution. At the end, I will give you a short conclusion and an outlook. We can see that we see for the axial testing, also for the axial torsional loading, a cyclic softening for both damage states, and also that a superimposed torsion or a torsion without a phase shift leads to faster damage development of the plasma. The cyclic softening is comparable regardless the damage states or the damage mechanisms are in general comparable, but we can see that the specimen with less forming-induced damage has a better performance. And also we can see that the manganese sulfides and also the pores are very relevant regarding the crack initiation and propagation, and that the 3D model generation can be used to determine the pore and sulfide distributions. At the end, I will give you a short outlook where we try to separate the damage mechanisms in the future because it's a cold form component, like dislocation densities are very important for the fatigue fracture, for the fatigue lifetimes. And that we try to get rid of with XRD investigations, where we look at the full width at half maximum to get a quantitative idea about the dislocation density. At the end, we want to correlate the fatigue test and the 3D models for different damage states or different states in the fatigue class, like at 75% of the lifetime. These are some reference publications, and at the end, I will thank the DFG for the funding of the subproject CO1 within the TRR 188.
Thank you.